Hi, thank you for joining us today. I'm Dan Rodier, Staff Scientist, Particle Measuring Systems, and my co-author is Glen Slayter, Intel Corporation. Today we'll be talking about controlling nanoparticle contamination in ultrapure water systems. I'd like to thank SEMI for hosting this conference, and I'd like to say a thank you to all the chairs and co-chairs who put in all the hours of reviewing and providing feedback for the presenters and the authors. Really appreciate it. Makes this conference a really useful asset to the community. It's a great place to share information and a great place to learn. So thank you. So we'll start off today with some background information on optical particle counters, just how they work, uh, some of the challenges with optical particle counting, and some of the advances in technology that have been made recently. And then we'll talk a little bit about the Intel PMS collaboration and what that kind of means to the particle counter side and what that means to the user side. It's an interesting perspective. And then we get into the data. We got lots of really good data here, looking at filter performance versus filter age, looking at nanoparticle removal from cartridge filters of different ages, ultra filters of different ages, and we've got some recent observations of nanoparticles in ion exchange beds. So looking at nanoparticle removal, but also looking at the wash down or rinse down of various types of mixed bed resins. And we'll talk a little bit about areas for future exploration, and then we'll summarize things. So liquid particle counters, optical particle counters, they all share similar components. This is a sort of a typical example here where you've got a laser, you've got some optics to focus the laser down onto a flow capillary made of glass or sapphire, and particles will pass through that capillary. And as particles pass through the laser beam, they scatter light. The scattered light is collected optically and focused onto a photodetector. And so you convert these pulses of scattered light from the particles into a pulse of photocurrent that we can measure. And so small particles scatter a little bit of light, create a small electrical pulse. Big particles scatter more light, create a bigger electrical pulse. And so we can compare these pulses to what we see for signal strength from calibration spheres. And so we can compare real world particles to equivalent scattered light from calibration spheres. And we can see this on an oscilloscope. I'll show you an example, a couple slides coming up, looking at 20 nanometer particles on the oscilloscope. Your basic light scattering curve here. If you looked at the slide on the right, you notice that that's log scale vertically, and then horizontally is linear. And you see you're right around 600 nanometers, it should be at 0.6 microns. You see it kind of changes from one regime to another. So at the larger sizes, particle diameter on the horizontal axis there, at the larger sizes, the intensity of the signal changes with the diameter squared. Once you get below the wavelength of light, in this case about 0.6 microns, the signal drops off very steeply. It drops off as a function of diameter to the sixth power. So if you look at the plot on the left, this is a log-log plot. It's easier to kind of see here these smaller diameters, but basically if you're changing an order of magnitude in particle diameter, so if you're going from a 200 nanometer particle to a 20 nanometer particle, it's going to scatter 10 to the 6th times less light, so 1,000,000 times less light scattered by a 20 nanometer particle than a 200 nanometer particle. And so this relationship means that if you want to go from even 30 nanometers down to 20 nanometers, you need to have a 10x performance improvement in your signal to noise to get that kind of particle counting performance. So it's quite a challenge to make small improvements in particle detection. So to do this, you need to have a comprehensive engineering approach. So you need to have solutions for both increasing the signal and reducing the noise. And we have these calibration spheres. This is shown on the oscilloscope here. These are 20 nanometer polystyrene latex calibration spheres. And so this is how we calibrate the sensitivity of our particle counter. You can see these are well above the noise level. So we have very good signal to noise and provide a very good statistically solid measurement. And even though these are calibrated with polystyrene latex spheres, the optical particle counters are sensitive to metallic particles of diameters less than 10 nanometers due to the differences in refractive index. We can see a lot smaller metal particles. In any case, the signal to noise is the key to performance and detectability. When it comes to the Intel PMS collaboration, we've been working together for a number of years. I really appreciate working with my co-author Glen. He's a tremendous resource and asset, and has a great knowledge base. His years in the industry working on UPW systems, very clean UPW systems. What PMS brings to the collaboration is our core metrology capabilities. We've got decades of particle counting experience, and we've got, really pushing the technology forward here. And so we collaborate with Intel to meet their requirements for fab implementation. So we come out with some technology, and we'll get pushback from Intel. They'll say, hey, you need to make it better. You need better signal to noise. You need to have better unit-to-unit matching. So if we're going to roll this out and make measurements in different areas, and we try to make comparisons in different areas, we need to be able to compare these units and know that we're seeing, apples to apples here. So really, the result of the collaboration is a better quality particle counter. And so this ability to partner together is a win for both of us, both sides. And with that, I'll turn it over to Glenn.
Thank you, Dan, and hello, everyone. My name is Glen Slayter, and I'm responsible for analytical sustaining and development at the Intel Corporation. I've been with the company now for nearly 20 years in a variety of different positions along that journey. This role brings with it a tight and never-ending crunch to drive down particle counts in our water with the ultimate goal of improving fab yields. Sustaining this effort requires constant engagement with our vendors at a technical and developmental level, with a focus not only on short-term needs, but with a constant eye on the next generation. This requires an ability to evaluate equipment in advance of release and provide feedback to help drive metrology to meet the demands of our semiconductor application. I value and appreciate that relationship with particle measuring systems. Dan spoke with you about the technical aspects of the UDI-20 particle counter, and I shift our focus toward the application side, with details of some filter evaluations and a mixed bed study. We entered into these investigations with an assortment of questions we hope to resolve. For example, what advantage does the UDI-20 gain over the UDI-50 in bringing visibility to particle baselines throughout our treatment system? Second, does the UDI-20 provide enough resolution to distinguish quality of individual filter housings of various ages? Third, can the UDI-20 characterize the overall efficiency of our filtration systems? 4, how does filter efficiency correlate to particle bin size as a filter ages? And last, could 20 nanometer baseline monitoring across specific unit operations like filters and mix beds enable a move from time-based maintenance to quality-based maintenance, potentially providing a cost benefit? In the next few slides, I will be sharing some results of our particle testing to better understand and characterize our various filtration systems. In generating these slides, I recognized right away that some obvious questions would naturally arise regarding the identity of our filter and resin manufacturers and ratings. Those are very relevant questions, but unfortunately, I'll tell you up front that I will be unable to share those details. Regardless of that, I'm confident that you'll benefit from the results, and I hope that it will trigger testing ideas that you might consider at your own facility. As you see from the schematic at the top of this slide, our filter particle study was applied to an array of 6 parallel cartridge filter housings with a common feed and a common product as shown. In this study, we utilized both the UDI-20 and UDI-50 optical particle counters to measure particle baselines on the product side of each filter housing, as well as the common feed and common outlet. Reordering the dataset by filter age, as shown in the chart below, exposed a strong correlation between particle counts and filter life. Remarkably, from just 1 to 6 months, we see a 12x increase in 20 nanometer counts and 50 nanometer counts at 6 months that well exceed our 20 nanometer baseline at just 1 month. In the next 2 slides, we will see the influence that this 6-month-old filter has on the overall system performance. Comparing the common feed and common product baselines in and out of the filter system by particle size enables us to characterize the overall filtration efficiency in relation to the rating of the filter. Overall, these UDI-20 results show strong filter efficiency, but noteworthy in the results is the measurable decrease in efficiency that occurs under 50 nanometers. This trend plots the filter efficiencies of each of the 6 filter housings in our study as a function of particle size to highlight the effect of filter age. The top line is our 1-month-old filter, showing the strongest efficiencies across the full range of particle sizes. From there, as we head down the trend, we see that filter efficiencies steadily drop as the filter ages from 1 to 6 months. As you can see, at just 6 months, efficiencies at 20 to 50 nanometers plummet from 94% to just 76%. This final chart illustrates a similar filter analysis as was just presented, but this time applied across 3 trains of ultrafilters. In this study, we blindly measured particle baselines of 20 nanometer and above at the product of 3 select filter UF skids, representing filter ages from 2 to 6 years. Reordering the baseline results by filter age, as shown here, illustrated a strong correlation to filter life, just as was demonstrated with the cartridge filter study. In this final section of our study results, we transition in the treatment of UPW from particle characterization in filtration systems to a deeper dive on ion exchange mixed bed particle loading, rinse down, and performance. While the primary function of an ion exchange resin is removal of ionic compounds, they have also proven quite effective in filtering out nanoparticle contamination. This trend illustrates the particle counts in and out of an ion exchange mixed bed. As you see here, the incoming water source contains particle baselines which are not only unstable, but are also orders of magnitude higher than the outlet. This is noteworthy because incoming particle counts can have a significant effect on mixed bed performance and risk to downstream filtration. This next slide highlights the 20 nanometer particle rinse down performance of new ion exchange resin from 2 different suppliers. The blue particle profile, indicated as resin A, exhibits a slow and gradual rinse that takes several days to reach the desired target for bringing the mixed bed back online. By contrast, resin B from a second supplier rinses down below target in just a few hours. The difference in resin rinse down performance as shown here has significant implications. In this example, resin B, the quicker rinse down shown in orange, is superior in several ways. For one, it has the benefit of a reduced rinse time for the mixed bed, getting the system back to normal production state in a timely fashion. Secondly, less rinse time means reduced UPW rinse consumption, which is a costly resource. And finally, quicker rinse down equates to a smaller particle load on downstream filtration when the mixed bed is placed online. The following trend highlights a benefit of monitoring system particle quality at greater analyzer sensitivities. In this example, the rinse down of an ion exchange resin bed was monitored simultaneously with both 50 and 20 nanometer particle counters. In this case, the less sensitive 50 nanometer counter in gray plummeted quickly, reaching the target threshold, permitting the bed to come online. The subsequent spike and second rinse down early in the 50 nanometer counter trend in gray shows the timing of that action. During the same period, the 20 nanometer counter in blue is clearly still experiencing a steep rinse down, only partway to its ultimate baseline. The area under the rinse curve highlights the total sub 50 nanometer particle throw, which was transferred onto and potentially through the final filtration system downstream. A move to 20 nanometer monitoring can help optimize rinse timing, which can reduce filter loading and have the potential to improve manufacturing yield as well. Okay, this last trend was a learning that we just had to pass along. In this image, the blue profile represents a typical ion exchange bed rinse down, whereas the trend in orange tracks the result of a less than ideal experience. During this resin rinse, a leak was soon discovered. When it could not be simply resolved, the rinse flow was shut off and the bed was fully drained. Unable to acquire necessary resources to complete the repair that afternoon, the resin was left to sit wet overnight. The next day, the leak was repaired and the rinse was resumed. However, the 20 nanometer particle counts struggled considerably over the next several days before finally reaching the expected baseline. In the end, the compromised performance was attributed to a persistent contaminant introduced while the bed sat idle. So where do we go from here? This study opens the door to countless opportunities to better understand and optimize our UPW treatment operations. For starters, this data has brought new perspective regarding our maintenance strategies. Seeing how particle concentrations increase with filter age enables us in the short term to optimize our maintenance frequencies to minimize particle baselines, while ultimately we work to qualify new filters with increased retention and longer life. Secondly, these results open the door to the possibility of transitioning some of our maintenance activities from time-based to quality-based, which could better optimize our filter life and capture measurable cost benefits. Secondly, we'd like to repeat these studies to strengthen this age correlation. Likewise, we could expand it out beyond 6 months with the ideal of characterizing filter and resin quality throughout its entire lifespan. It would also be interesting to add the resin mix bed into the age evaluation, testing beds of various ages to see how particle performance changes as a function of time. And finally, we could extend these particle characterization efforts across other unit operations. We could begin by segmenting every major unit operation to expose the primary sources of particle adders. From this segmentation, we could narrow in on the highest sources to explore improvement opportunities. And finally, we could repeat that same segmentation from fab to fab to highlight differences and drive low-performing systems to higher standards. And with that, Dan, I turn it back to you.
That's great. Thanks, Glenn. Appreciate you sharing the data and getting your perspective on that. To summarize, collaboration, in this case, collaboration between a particle counter manufacturer and a device manufacturer, results in better metrology. So by working closely together and understanding the needs and how the product needs to perform, we're able to come up with better metrology both now and in the future. And so we encourage collaboration with device manufacturers, and we look forward to doing more of that as we go into the future. Our objective today was to share some results from this particular collaboration we have with Intel. And we had a chance to go through some really interesting data. We went through the filter data first, looking at the cartridge and ultrafilter data, showing that strong correlation between duration of usage and particle filtration efficiency. This is particularly true with the cartridge filters. And by transitioning from 50 nanometer to 20 nanometer particle metrology, makes it a lot easier to detect and track those changes in filter performance. In fact, the cartridge filter performance change is really only visible after about 6 months of usage. And by that time, the contamination at 20 nanometers had increased by 1,200% in those 6 months. So the small particles start breaking through the filters a lot sooner than the large particles do. And the only way you're going to know that is if you're monitoring that. We also looked at the study of the ion exchange resin, and it's highlighted some significant differences in quality between suppliers. It also showed that the ion exchange resins are really good at removing nanoparticles. So you're looking at orders of magnitude removal, relatively speaking. And so that was kind of an interesting find. Others have reported similar results at a little bit larger particle sizes. Rinse down time differences, we saw that from vendor to vendor. We also see a difference between your decision when you decide that the rinse down is complete and you want to bring the unit online. And if you're monitoring at 50 nanometers, that point comes a lot earlier. But if you're monitoring at 20 nanometers, you can see that the bed's still rinsing, still flushing down, continues to flush down for hours more after the 50 nanometer data looks clean. So by monitoring at 20 nanometers, you can keep that rinse down going until you know it's clean at 20 nanometers, and you can reduce loading up your downstream filters by bringing it online a little bit too early. We also have several other joint projects in process. Our primary focus area is yield improvement with all of this work. And water touches pretty much every part of semiconductor manufacturing. And so it's very important to have very clean and very stable water quality. And as we move forward, we're really following the data. The data is we're learning as we go, and the data is leading us. And so it kind of opens our eyes. We see some opportunities, new opportunities for continuing to improve our yield enhancement here, improve the quality of the water product. So just want to say thank you for your attention today. Please join us for a live Q&A session on Wednesday, the 12th. Note this is Eastern time. I'd love to get your questions, have some good discussions going about all this great data, and some thoughts and your input as well into the process. So hopefully we'll be able to meet up at that time. If you're unable to join us for the live Q&A, please feel free to contact us at our email. Both Glenn and I have our email listed here. We'd love to hear from you and any questions you might have or suggestions or thoughts. Thank you very much. Have a good day.